Okay. Um, okay, I'll start. It's an honor to be the first presenter. My name is Dongyeon, and our team members are Yerim, Eunyi, and Wang Hee-Hwan. I'll cover the contents in this way. We will use a term called intrinsic dimension. I think you are not familiar with it, so I will spend some time for introducing the term and show some of the results that we made. So let's start with this one. So it is well known that the high dimensional data, such as natural languages and images, consists of the low dimensional structure. So if we consider this kind of data, we can see that the data samples are located in the higher dimensional space, but actually we can position each sample with a lower dimension. So, but actually natural languages and images are having the much higher dimension. And previously, we didn't know how to handle this kind of data. But now we can using the deep learning. Deep learning is working very efficiently for this kind of data, but we don't know why and how it is working. So we are using the term called intrinsic dimension to find it out what is going on inside it. So this is the goal of the project. We are trying to understand the higher dimensional data and representation with intrinsic dimension. For the first step, we find the accurate and robust ID estimators. And the second step, we will show some how this ID estimation can be utilized in the real scenarios, such as data augmentation and transfer learning. ID is defined as the minimal number of coordinates required for describing the distribution of the data representation. So if we bring these two figures, then the ID value for the left one would be 1 because all the data are located at the curved line, and the ID for the right figure would be 2. There are a few other features that ID have. And moving on to our comparison part, we chose 4 baselines for ID estimator, GeoMLE, KNN, 2NN, and MLE, and evaluate based on the estimation accuracy and the robustness. Since we don't know the ID label for the real images, we use the BigGAN to make a synthesized image. So these are a few samples. You can see that the left two has a lower diversity and the right two figures have the higher diversities, which means that the left one is sampled from the lower latent dimension. The right ones are sampled from the higher latent dimension. So using those samples, we measure the ID estimation accuracy, and 2NN MLE shows the best accuracy among the other baselines. And move on to the robustness part. We figured out how ID estimation stays stable for resized images and sampling rates. And the result shows that the 2NN works a little bit better for the higher data, and the MLE is working better for the lower dimensional data. So in sum up, we are using the 2NN for our base estimator, because it is shown that it's accurate and robust. And compared to the MLE, which is also showing the good performance, 2NN is more computationally efficient and have required no hyperparameters. So this is the equation how we can calculate the 2NN, but I will skip this part. And conceptually, it is using the ratio between the first nearest sample from the given sample and the second nearest sample. So using the distribution of these two, we can estimate the ID value. So when we are using ID at the data augmentation, in this experiment, we use 3 different kind of augmentation methods. And if it is applied to the raw data, then we can see that the ID for the raw data is showing the lowest value, and the ID for the other augmentation is showing the higher value. And this is a kind of interesting experiment that we can do. Since data is flowing from the input to the output, and we can capture the feature representation from the intermediate layer, we can plot in this way. So from the figure, we can see that the line or the data point with the no augmentation is showing the higher value at the intermediate layer, while the lowest value at the dense layer. And we could also correlate with the validation accuracy. Since we don't have enough time, I will move on to the transfer learning part. And we also see that the how ID pattern is changing while the transfer learning is being processed. So in sum up, we compare the ID estimators and shows how this can be utilized for the data augmentation and the transfer learning. Okay, thank you for listening. So is there any question? I think I rushed too fast.
Any question? Okay, thanks.
Okay. Or if you have a remaining time, can I like explain a little bit more for the result, or just move on?
I think we are almost done.
Okay, I see. Thank you.
Okay, thanks.